So we've been talking about equilibrium, 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 lots of equilibrium things. We've been talking about what I would term general equilibrium, meaning how do you set up rice tables? How do you set up K expressions? What kind of math do you do to fill in ice tables and rice tables and that kind of thing? We've talked about equilibrium means when the rate of the forward is equal to the rate of the reverse. Yep, that's the definition of equilibrium. Well, it's time now to talk about a specific type of equilibrium. And we're going to talk about solubility equilibria. Throwing it back, way back to chapter 4, which you studied in first term general chemistry. Back in chapter 4, you had to learn the solubility rules. And back in chapter 4, we said these guys are soluble when they hook up with pretty much anything. There are a few exceptions to these solubility rules. Chloride, is soluble with everything that it partners up with. Every cation that chloride partners up with, except for silver, mercury, and lead. Bromide is soluble when it partners up with everything except for silver, mercury, and lead. Iodide is soluble with everything except when it partners up with silver, mercury, and lead. Sulfate is one of those that is soluble with most things, but there are a few exceptions to that as well. You may or may not remember, but if we have a +1 cation hooking up with a -1 anion, it's very likely that that's a soluble compound. Is it always the case? No, because silver and chloride is a +1 and a -1. But it's very likely soluble when you have a +1 hooking up with a -1. If you have a +2 hooking up with a -2, it's very likely not soluble. Also known as insoluble. So a +2 with a -2, probably not soluble. Look. A 2 minus. And anything is insoluble except for these things. And alkali metals are the first column of the periodic table, the first group. So that's like lithium, which is a 1+, sodium, which is a 1+, potassium, which is a 1+. Yeah, so when carbonate, this guy, hooks up with a 1+, it's soluble, but if it hooks up with a 2+, probably not. So, interesting. If you have a +1 or -1, probably soluble. +2 or -2, probably not soluble. +2 or -2 or greater, probably not soluble. That's very general rules. Why do I say these very general rules? Because I hate memorizing things, and I don't want to sit down and memorize this table. I want to say, if it's +1, -1, probably soluble. If it's +2, -2, probably not. What if it's something like a +1 and a -2? Like lithium sulfide. That's going to be Li2S. Because one of them has a charge of 1, it's likely that that thing is soluble. Here's where I'm going to find out solubility rules. Sulfides are almost always insoluble unless they're with an alkali metal, and lithium is an alkali metal. If we reverse those roles and say, what if it's a -1, like a chloride, with a +2, like a calcium? Well, chloride is soluble with almost all things, only it's not soluble silver, mercury, lead. Calcium is not one of those. So this one is also soluble. I got a -1 and a +2. Anytime you have a +1 or -1, whether they're both +1 and -1, or whether they're partnered up with a +2, -2, +3, -3, whatever. Anytime you have a +1 or a -1, it's probably a soluble compound. But when both charges are greater than +1, it's probably not a soluble compound. Okay, I've talked on this slide long enough. Moving along. Calcium chloride is soluble. According to my solubility rules, calcium chloride is soluble. Because it's soluble, we treat it as limiting reactant. What the heck does that even mean? If we write the equation, CaCl2, solid, and we add some water, and I'm putting it on the arrow for a reason, but we add some water, it means it will dissociate into Ca2+ ions and Cl- ions, aqueous ions. When this splits apart, you get 2 chloride ions and 1 calcium 2+. In a beaker, it means we dump solid calcium chloride into that beaker. Isn't it lovely pictures I got here? we see some Ca2 pluses floating around in solution, and we see 2 Cl minuses for every Ca2 plus floating in solution. It's completely soluble. Okay, hold that thought. I'm not quite done talking about that, but I'm done for a second. Calcium sulfate, that's a +2 and a -2, not soluble. Insoluble ions are treated as equilibrium. What the heck does that mean? CaSO4, solid, plus water, yields Ca2 plus and SO4 2 minus. But, you said it's not, yeah, hold on. It's treated as an equilibrium. When a reaction is at equilibrium, can you have 0 products or 0 reactants? No. So when we say that this reaction is treated as an equilibrium, we call it insoluble, but we really mean it's not very soluble. What the heck? We mean we're going to have a tiny little amount of calcium ions in solution and a tiny little amount of sulfate ions in solution, but not very much at all. We'll have small amounts of these. Mostly it's solid at the bottom. So a beaker, if we have some calcium sulfate, this is on a watch glass, isn't that a cute little watch glass? You dump it in that beaker, you end up with a bunch of calcium sulfate that sinks to the bottom. But you will have a little tiny amount of calcium 2 plus in solution and a little tiny amount of sulfate 2 minus in solution. Okay, one thing that I have done incorrectly thus far. This guy is a straight arrow. It's not a back and forth arrow. This guy is a straight arrow. It's not a back and forth arrow. Is that correct? Well, we're going to start specifying that if something is treated as a limiting reactant, we will draw it as a straightforward arrow and a straightforward arrow only. What we're doing by drawing the straightforward arrow only is signifying that that reaction goes to completion. There's going to be no solid calcium chloride at the bottom. That does not exist. Calcium chloride at the bottom does not exist. If we treat it as an insoluble compound, there will be calcium sulfate at the bottom. We treat it as equilibrium. We draw that as reversible arrows. So limiting reactant on the left because it's a soluble compound. Equilibrium on the right because it's a not soluble compound. Okay, I'm taking a real long time on all the slides so far. Ionic compounds are either soluble or not soluble. Back when we learned solubility rules in chapter 4, we said that. So looking at the solubility rules, predict the solubility of the following ionic compounds. I got a +2 and a -1, almost certainly soluble. So I'm going to say soluble unless I have memorized it's one of the exceptions. It's not. And being soluble means floating around calcium ions and floating around chloride ions. Okay. Calcium sulfate, that's a +2 and a -2. It's the exact same 2 examples we just talked through. I know. But that one, +2, -2, very likely not soluble. Yeah, not soluble. But, there are still a few ions in solution. A little tiny amount of ions in solution. Iron hydroxide. Iron hydroxide is a +2 and a -1. Iron 2 hydroxide, let me name it properly. The rules say it's not soluble. Hydroxides are one of those -1 exceptions where most of the things are not soluble. But a few ions exist in solution. A little tiny amount exists in solution. Note that there's 1 iron and 2 hydroxides because they dissociate in that ratio. Okay. The amount of solid present does not affect the concentration of ions in solution. I have tried to draw this picture to show lots of solid, 2 irons, 4 hydroxides. A little bit of solid, 2 irons, 4 hydroxides. Because the amount of solid present in solution is determined by the K value, the equilibrium K value. The amount of solid does not matter. The concentration of ions in solution are going to be the same as long as there is some solid present. That's kind of an important point that students don't always understand as important in the beginning. Okay, so let's talk about solubility equilibria. So all that stuff was solubility rules and whether we treat compounds as soluble or insoluble. If we treat something as insoluble, we're going to talk about equilibrium stuff associated with those insoluble compounds. And we're going to have to calculate the concentration of ions in solution of insoluble compounds. Do you expect these to be big numbers if they're insoluble? I hope not. So AgCl is one of those insoluble exceptions. So we treat it as equilibrium. There's a little tiny amount of Ag plus and Cl minus in solution. If we were to draw a picture of it, we would have a bunch of solid AgCl at the bottom and a little tiny amount of each of the ions. I drew 3, but I could have stopped at less than 3, but I did 3. Okay. If we write the K expression for this reaction, the K expression would be the concentration of Ag plus times the concentration of Cl minus divided by AgCl. No, divided by AgCl, because AgCl is a solid and solids don't show up in K values. So there's my K thing. We might want to call it Kc, except we're not gonna. Because this is our first time looking at a specific type of equilibrium. We're going to call this Ksp, where Sp stands for the solubility product constant. You see why it's solubility product constant. Pen, where are you? Solubility product, Ksp. So the solubility product is always an equation starts as a solid and breaks down into ions. It's not a Ksp equation if it's ions coming together to create a solid. This is not a Ksp. That should be an equilibrium. And I can't fit all my writing over there. This is not a Ksp that I just wrote in blue. This is the reverse of the Ksp reaction is different. Okay. So let me get all that gone. The Ksp value for AgCl is 1.6 times 10 to the negative 10. That's a value that's universal for AgCl. You can look it up in a table. That is a constant. It's a solubility product constant for AgCl. If you looked up the solubility product constant for iron 2 hydroxide, it's a different number. These are all unique to the reaction in question. Practice writing solubility equilibria expressions. Here are 3 examples. I'm going to write 2 of them, and you're going to write 1 of them. Solubility product constant stuff means solid breaking down into ions. Break it down. Yeah. Gotta do something to keep myself entertained while I'm doing this mess. Mg2 plus AQ, 2 OH minus AQ. We get aqueous ions when that insoluble compound breaks down. Our Ksp expression for this guy would be Mg2 plus times OH minus squared. That's easy. That was so fun. How about some more? Ag plus AQ plus CO32 minus. You got to remember those polyatomic ions. Is there a problem here? I hope you detected there's a problem here. I got 2 Ag pluses. My Ksp would be Ag plus squared. Plus squared. I'm putting the thing in the wrong place on the brackets. CO32 minus to the first power. You got to do this one. I'll grade it for you later. I think you got it. So I said the solubility product constants can be looked up in a table. Look what I found. A table of solubility product constants. And silver, where are we? Silver chloride, 1.67 to the negative 10. Yep. Depending on the resource that you use, sometimes these values are slightly different. A tiny bit different. When you get to numbers as tiny as 10 to the negative 33, a little decimal here and there makes a difference. So a little rounding here and there makes a little difference. So sometimes they're slightly different if you look at a different resource. Okay, moving on. So if we work on relating this new Ksp stuff to some old information that we have, and we try to answer the question, will a precipitate form? If we are given ions and asked, do you get a solid when you put those ions together? We can calculate Q for the given reaction to determine if a precipitate forms or not. If Q is less than Ksp, that solution is said to be unsaturated and a precipitate will not form. If Q is equal to K, you are at equilibrium. It's called a saturated solution officially. It's just about to the point of precipitating. Officially, when Q equals K, there is no precipitate present. It's just on the cusp of about to form a precipitate. If Q is greater than K, yeah, it's supersaturated. You are absolutely going to precipitate. That's how the Q stuff relates to the K stuff. Let's do some problems and wrap this puppy up. The solubility of Ag2CO3 is this. The equation is that. What's the value of KSP? Okay, question number 1. Is this a KSP equation? Yes, because it starts with a solid and it breaks down into ions. This is absolutely a KSP equation. Solid into aqueous ions. Yeah. So I'm going to start by writing my KSP expression for this reaction. That's obviously silver plus squared times carbonate. No Ag2CO3 because it's solid. We don't care. How do I determine the value of KSP? Well, when in doubt, make a rice table. It's the answer to so many of our problems all semester. I gotta rewrite the equation because I did not plan appropriately, so I can't put my rice table up yonder. How much initial concentration of Ag2CO3 is there? It's a solid. We don't care. Because solids are never ever found in equilibrium expressions, we don't actually care how much you started with. As long as some solid is present, we don't care how much. There's none of this and none of that. We're going to lose some of the solid, but we don't care. We're going to gain some of the ions. At equilibrium, it's going to be 2x squared times x. Once again, note the 2x is all squared, and when you square that whole thing, it becomes and simplifies to be 4x cubed. Now what? I don't know what to do from here. This sentence up here that I have ignored so far, the solubility of Ag2CO3 is 1.27 times 10 to the negative 4th molar. The solubility, they're telling you the value of X. That's really what that is. The solubility is telling you this right here. It's telling you how much Ag2CO3, silver carbonate, it's telling you how much silver carbonate is dissolving in solution. It's telling you the change in silver carbonate. So it's really telling you the value of X. If you look throughout the textbook, instead of X, the textbook says the solubility, using the letter S, equals 1.27 times 10 to the negative 4th. X, S, whatever, it doesn't matter. We know the value of X. So I'm going to plug in, and I'm going to switch colors so that maybe you can follow along a little bit easier. 4 times 1.27 times 10 to the negative 4th cubed. Plug and chug, and that's going to tell me my KSP value. That is going to be my KSP value. If I did my math properly, that's 8.19 times 10 to the negative 12. Please pardon my dear Aunt Sue, my dear Aunt Sally. Make sure you're following the order of operation stuff properly. 8.19 times 10 to the negative 12. That's silver carbonate. Let's see if we got it right. Silver carbonate, silver carbonate, silver carbonate. 8.1. Ooh, look at us, look at us. We got an 8.2 times 10 to the negative 12. When it's negative 12, that's close enough. Yeah, it's good. Okay, final example. This is a long video. If 2 milliliters of 0.2 molar sodium hydroxide are added to 1 liter of 0.1 molar calcium chloride, will a precipitate form? What? If we have a solution of calcium chloride, it's a soluble thing, calcium chloride. I'm picturing that in my mind's eye. Calcium chloride dissolved in solution. I'm going to add sodium hydroxide to it. And the reason I pulled out hydroxide is because when hydroxide hooks up with calcium, it's going to make an insoluble salt. So the sodium is a spectator. We don't care about the sodium, actually. Hydroxide is going to hook up with calcium and make an insoluble salt, potentially. When you add those hydroxide, do you get this, where everything's dissolved, Or do you get some of this? Calcium hydroxide at the bottom and ions. You're still going to have a little baby amount of calcium, 2+, and maybe even a little baby amount of hydroxide and a little bit of chloride left over. I should be official and draw this many chlorides, but I didn't, and I'm not going to now. Sorry. The only possible precipitate is calcium hydroxide. So when we're asked, will a precipitate form? That means find Q. Because if Q is greater than K, we will have a precipitate. So find Q. In order to find Q, we need to know the equation that's under consideration. That means we need to know the KSP equation for solid calcium hydroxide. And that's this equation. So KSP/QSP is calcium times hydroxide squared. So we need to know the concentration of calcium and the concentration of hydroxide. Well, if it's 1 liter of 1 molar calcium chloride, that means the concentration of calcium is 0.1 molar. If it's 2 milliliters of 0.2 molar sodium hydroxide, we have to do a little math with this one. That's because it's 2 milliliters being added into 1 liter. A dilution is happening between these 2 milliliters and 1 liter. A dilution is happening. So, I kind of want to click to the next slide so that I can have more space. Maybe I can fit it here. Okay, so I can think of this one 2 ways. And I can say 0.002 liters, because that's 2 milliliters, times 0.2 moles of hydroxide per 1 liter gives me 0.004, and I might not have enough zeros. I think it should be one more. Let me double check with the calculator. Moles of hydroxide. Calculator, where are you? So, yep, I was right. 0.0004 moles of hydroxide divided by 1.002 liters officially because it's diluted into that volume now. I'm going to round and say 4 times 10 to the negative 4th molar. That's the concentration of hydroxide in my new beaker where it has been diluted. My concentration of calcium is not going to change when I add. It's not going to change significantly when I add 2 milliliters of stuff to it, but my concentration of hydroxide does change significantly when you add it to a 1 liter flask. Okay, so I got 0.1 molar calcium times 4 times 10 to the, 4 times 10 to the negative 4. I left off the negative 4. 4 times 10 to the negative 4 hydroxide squared. I do that math and I get 1.6 times 10 to the negative 8. Q equals 1.6 times 10 to the negative 8. And K, that I can look up in a table, is times 10 to the negative 6. Q is smaller than K, and when Q is smaller than K, no precipitate. Whew, this was a doozy. It's going to be a fun one. Solubility, man. We got this.